Hello class. Today we're going to be talking about aromatic hydrocarbons and substituent groups. So we touched on alkyl groups as substituent groups, other hydrocarbons, but there are a ton of different things you can add to hydrocarbon chains. We're only going to explore a very small portion of them, but for right now let's start with aromatic hydrocarbons. One of the most diverse and important classes of organic compounds. So, everything we've dealt with up to this point has been considered an aliphatic hydrocarbon. Right? Our straight chain hydrocarbons, those are considered aliphatic. Aromatic hydrocarbons, on the other hand, they contain ring structures with double bonds, and they're called aromatic because they often have an odor. So a lot of these aromatic compounds, well, most of them are responsible for the things you smell, the things you taste, and responsible for a lot of things in your day-to-day life. Now the most common aromatic is benzene. Benzene rings are one of the most common things we see within biological organisms, within organic compounds. Now, benzene is C6H6. It is a 6-carbon cyclic ring, but you're going to notice that if it was just cyclohexane, the molecular formula would be what? Well, it would be C6H12. It's not. It's C6H6, ends in -ene. So what does that tell you? Well, it tells you there's a bunch of double bonds. So, benzene is very unique. The carbon-to-carbon bonds within benzene have a length of 1.4 angstroms. Now, single bonds have a value of 1.54, double bonds have a value of 1.34, and triple bonds are even closer together. But the benzene ring lies somewhere between a single bond and a double bond. Right? It lies somewhere in between. This is one way we represent benzene, but benzene really is a 6-carbon ring with alternating double bonds. Now, due to the way double bonds work, we consider these shared electrons to be delocalized, is the term, because these double bonds can move, right? They're delocalized, so we draw them like this. So these shared electrons of these double bonds are shared amongst all of the carbons. If that doesn't really make sense to you, it's okay. You'll learn all about that if you take a university level chemistry class. Now, from this point forward, I will be representing benzene rings like this. So every time you see this inner circle, you know you're dealing with a benzene ring, right? They have these delocalized electrons. Now, when it comes to naming these, there's two separate cases. The first case is going to be that your benzene group is a substituent group, right? It is part of a larger chain. The second case is that benzene is your backbone, it is your parent, and then you will name these substituent groups that come off of it. So case number one. Here we have a benzene ring attached to a hydrocarbon that is 7 carbons in length. So we are going to treat this benzene as a substituent group, and the name of that group is phenyl. So how would I name this? Well, our carbons are 1, 2, 3, 4, 5, 6, 7, so we have our benzene at carbon 4. So this would be 4-phenylheptane. So we treat this benzene ring, if it's on a long hydrocarbon chain greater than 6 carbons, we treat it as a substituent group just like any of our other substituent groups. Now, you probably won't get a scenario like this in a grade 11 course. Really, we didn't really learn the specific names of branched side chains, and you won't really until university level. So if you were to see something like this on a test at a grade 11 level, you would treat this as the backbone. So if you have a branched side chain coming off of a benzene ring, you would treat this here as your parent chain. So as a result, we have the phenyl group here on carbon 1 and the methyl group here on carbon 3. So if we were to name this, this would be 3-methyl 1-phenyl butane. Now again, alphabetical order still applies to those substituent groups, M before P. Right? And you still want to label them such that your substituent groups have the lowest numbers possible. What about an example like this? Is this 2-phenylheptane or 6-phenylheptane? Again, I just said it. You want to make sure that your substituent groups have the lowest number possible, so this is 2-phenylheptane. Do not forget about that rule. It is one of the most common mistakes that students make. What about the case number 2, where aromatics, or where benzene rings are your parent chain, right? They are your backbone. In these cases, there is 3 possible scenarios. Your benzene ring has 1 substituent group, 2 substituent groups, or 3 substituent groups. In the case of a monosubstituted benzene ring, it's pretty easy. You don't need to number it. Why don't you need to number it? Well, it's always going to be a carbon 1. So in this case here, this is going to be a benzene ring with a methyl group. Now, how do we name these substances? Well, we will use the suffix benzene. So this here would be methylbenzene, right? This one would be methylbenzene. This ring here, benzene ring, would be 1,2-dimethylbenzene. Now we're about to learn a new strategy for disubstituted, one that you do have to use, because in organic chemistry, we have a very specific way of naming these disubstituted molecules. But that's the old way you would have learned. For this polysubstituted, we have methyls at 1, 2, and 3, so that'll be 1, 2, 3 trimethylbenzene. So here we have methylbenzene, ethylbenzene, and chlorobenzene. One thing that we really aren't going to have time to touch on, we won't have a chance to look at all substituent groups, but with halogens, they can be substituent groups on hydrocarbons. It is pretty straightforward. If you see chlorine, it's chloro, bromine's bromo, iodine is iodo, fluorine is fluoro. So it's pretty straightforward. Those are the main ones you're going to see. If it comes off of any hydrocarbon, again, you do need to number it and place in alphabetical order. Now, disubstituted are a little bit more complicated. So we do have a specific naming nomenclature when it comes to disubstituted. If you have 2 substituent groups side by side, we call this ortho. So if this was another methyl group right here, that would be ortho dimethylbenzene, right? Or maybe it's here and here, right? That would be meta-dimethylbenzene or para-dimethylbenzene. So ortho side by side, meta 1 step removed, para opposite ends. So if we look here, this is a great example of ortho dichlorobenzene. You don't have to write out ortho, you can actually just write O. This would be meta, you can just write M. And this one is para-dichlorobenzene, you can just write P. So when you are naming these, I do not want you to use our old method, right? I want you to use the specific naming nomenclature for disubstituted benzene rings. Okay, so really, organic chemistry is a little bit messy because this is the preferred method, but technically, like, this isn't wrong, right? This option here isn't wrong. Although this is orthomethylbenzene is the preferred method. Alright, so for poly, we just use our original method, right? So this one here would be 1,2,3-trimethylbenzene. So I've touched on just a few of the substituent groups. We're going to learn a couple specific ones right now, but there is a whack load of substituent groups. Right? You have alcohols, ethers, epoxides, haloalkanes, aka your halogens as substituent groups, aldehydes, ketones, carboxylic acids, acid anhydrides, esters, amides, acyl halides, amines, nitriles, imines, isocyanates, azo compounds, thiols, arenes. And this is just a small subset of the entire list. So we are only going to sample a couple of these right now. You won't really learn more about them until you take organic chemistry at a university level. So, we call all of those things I just named functional groups. And the functional groups are very important because they do drastically change the reactivity of your hydrocarbons, and it changes a lot of different things about it. Now, of the functional groups, the only ones we are actually going to explore right now are going to be alcohols, acids, and esters. Okay, that's it. Alcohols, esters, and acids. Now, that doesn't mean you shouldn't take some time right now and identify some of those other substituent groups that I listed previously. So take a second, try to pick out the substituent groups listed here. Now, you should find this. Okay? Again, the only ones we're going to learn in more detail in regards to naming are going to be alcohols, carboxylic acids, and esters. Alcohols are hydrocarbons that have an OH group, a hydroxide group, added. The most simple of which would be this one here, methanol. Methanol is brake line antifreeze. You know, if you have a distillery, since it has a lower boiling point than ethanol, when you are distilling, methanol comes off first. It's a byproduct of distilling. And methanol is very dangerous. You wouldn't want to drink methanol. Small doses, it'll make you go blind. Large doses, you will die. Now, of the alcohols, you're probably very familiar with ethanol. Ethanol is the active ingredient in booze, right? In beer, wine, spirits. Ethanol is a drug, and what it does is it does, start to shut down parts of your brain. It is a depressant. Now, if you drink too much alcohol, you can actually die of overdose. It can stop the signals going from your medulla to your intercostal muscles and diaphragm. You can stop breathing and you can die. So although methanol is very toxic, ethanol is also toxic for the human body. Very dangerous drug, ethanol. Kills brain cells, highly addictive, and it has a horrible cost to society. Of all the drugs we could socialize, ethanol was probably one of the worst. Now, how would I name these here? Okay, how would I name this one here, and how would I draw this one here? Let's take a brief second to practice. So, with this group here, how many carbons do I have in this compound? By the way, if you ever see brackets with a number outside, that is saying that this subunit is repeated 5 times. So this is CH3 bonded to a CH2, bonded to a CH2, to a CH2, to a CH2, to a CH2, and then to a hydroxyl group here. So this is 6 carbons with an OH. What would we call that? Well, we're replacing hexane, that suffix, with ol, right? With dash OL. That's how we show that as an alcohol, right? So in this case, this would be hexanol. And we do need to label where it is in the hydrocarbon chain. So in this case, it would be 1-hexanol. Probably not the best example because I didn't show you the condensed structural formula, but we will show it when we draw this one out here. So this is 1-hexanol. Now, if we look at this one here, 4-methyl-2-pentanol, we can see here that we put the alcohol on carbon 2. Again, it doesn't really matter which way we draw this, because it would be the same either way. We could have put the alcohol group here and the methyl group here. It would have been the same regardless. So that's what it looks like. Now, if you had multiple hydroxyl groups, let's say we had a hydroxyl group at 2 and at 4, you would call this, a 2,4-pentadiol. So we're not going to get too much into that, but it is possible to have more than one of these alcohol groups per organic molecule. All right, what about acids? Well, this here is carboxylic acid. It's a carbon double bond to an oxygen with a single bond to a hydroxyl group. You probably have seen this before. If you've taken biology, you for sure have seen this before, right? They're present on fatty acids, right? A fatty acid is just a carboxylic acid group with a string of hydrocarbons attached to it. You may have also seen it in amino acids. With amino acids, you have that amino group and that carboxylic acid group. So, if we have in carboxylic acid, the suffix for this functional group is oic acid. So if we had a 5-carbon chain, for example, with that carboxylic group, that would be pentanoic acid. Maybe it's just a 2-carbon chain, so it's ethanoic acid. You get the idea. This one here is as simple as it gets. So if this R group here was just a hydrogen, that would be methanoic acid. Alright. When naming these, the carboxyl group is always the first carbon. Right? So whenever we name a carboxylic acid group, carbon 1 is always going to be that carboxylic acid group. So methanoic acid, what would ethanoic acid look like? 2 carbons now, right? 2 carbons, it would look like this. What about propanoic acid? 3 carbons. Well, it would look like this. When we are giving carboxylic acids alcohols, I will not be giving you any that are really heavily substituted, especially carboxylic acids. You're not going to really see any substitutions because we are going to be showing you now how to make esters. Esters are the result of a reaction between an alcohol and a carboxylic acid. They do the most common biochemical reaction, which is dehydration synthesis. They are one of the most common compounds in society. They are responsible for many tastes and odors in foods. There's a really good lab you can do, an ester lab, where you take a really stinky alcohol, a really stinky carboxylic acid. They're horrible in stench, right? Ugh, they're really bad to work with. You mix them together, and then you get like banana flavoring, right? So in no way, shape, or form is what you start with what you're going to end up with. A lot of those artificial flavors and stuff come from these types of reactions. A lot of drugs are the result of esterification, the making of esters, and a lot of clothing. Whenever you wear polyester, which is becoming more and more prominent in clothing, that is an esterification reaction. Also, adhesives and paints, very common to have esters. So, esters, they're formed by esterification, which is going to be the dehydration synthesis reaction between carboxylic acid and alcohol. If you notice here, this group loses an H2O to join them together. So you'll have two molecules that get joined together by the loss of water, hence dehydration. Now when we're naming these, it's a little tricky, but once you get the hang of it, it's not that bad. So we take the initial alkyl group from the alcohol. So let's say it was methanol. You'll take meth from that. And the final word from the acid, and then you replace the ick of the acid with an ate. So instead of, for example, let's say we combined methanol and ethanoic acid, right? So methanol is our alcohol, ethanoic acid is our carboxylic acid. Well, we would take that ethyl, right, the alkyl portion of that alcohol, and we're going to combine that with the name of our acid with a little change to the end there. So that would be methyl ethanoate. Instead of ethanoic acid, it is now ethanoate. So ethanoic acid plus ethanol would give you ethyl, ethanoate, and water. Right? We have our 2-carbon alcohol, our 2-carbon carboxylic acid, ethanol, ethanoic acid. When these combine together through dehydration synthesis, you form ethyl ethanoate and H2O. Okay, ethyl ethanoate and H2O. So let's now do a couple practice problems with everything we learned today. Let's review aromatic hydrocarbons first. How would I name this compound here? Well, we have a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain attached to a benzene here at carbon 1, 2, 3, 4, 5. How would we name this? Well, this is one of those case 1 situations where we are going to treat benzene as a functional group. Okay? You know what? Let's make this even a little bit more complicated, because why the heck not? Let's add a double bond right here. Because again, this doesn't have to be just straight chain alkanes. There could be alkanes and alkynes as well that have these substituent groups. So let's now name this sucker. So, what were the rules when it came to alkenes? Well, you always got to give that double bond the lowest number possible. So when naming this, but if this double bond wasn't here, we would name this 1, 2, 3, 4, 5, 6, 7, 8, right? Because that would give our carbons the lowest numbers possible.
Next to the front entrance, please.
However, in this case, since we have a double bond here, we need to label this 1, 2, 3, 4, 5, 6, 7, and 8. Okay? So we have a double bond on carbon 1, we have a phenyl group on carbon 4, we have a bromo group on carbon 5, and a methyl group on carbon 7. So what is our parent chain? Well, our parent chain in this case is what? It is 1 octene. And what are our substituent groups? Well, we have substituent groups at 4, which is 4-phenyl. And we have a substituent group at 5, 5-bromo. And we have a substituent group at 7, which is 7-methyl. So when I combine this all together, keep in mind our substituent groups do need to be listed in alphabetical order. I come up with a compound name of, we have 5-bromo, we have 7-methyl, 4-phenyl, 1-octene. Okay, so yes, it is an extremely long name, but again, we are just following the same rules over and over again. Let's look at our other example I have up here. This is a case 2 situation where our benzene ring is our parent chain, right? It's our main chain. So, in this case, we have a methyl group here and an ethyl group here. Now, you may be tempted to call this 1-ethyl, 3-methyl, but I don't want you to use the conventional naming system. I want you to use meta, ortho, para. Okay, so what is this one here? Well, it's not ortho because they're not side by side. It's not para because they're not opposite each other. This is meta. So this compound here, we have a methyl group and an ethyl group. Ethyl comes before methyl in alphabetical order. This would be meta, or M, ethyl, methyl, benzene. Right? We're still using benzene as our suffix here, as our final word, because it is our parent chain. Okay? So again, you do need to use the the meta, ortho, para naming system with di-substituted benzene rings. Now let's look at an example of an alcohol, a carboxylic acid, and the resulting esterification reaction. So what will we call this here? What is this molecule called? Well, we see that hydroxyl functional group, and it's attached to a 1, 2, 3, 4 carbon chain. So what is the name of that molecule? Well, without the hydroxyl group, that would be butane. With it, now that's butanol. So this is 1-butanol. And what about this substance here? This has 1, 2, 3 carbons. And here we see this carboxylic acid group. So again, we add the oic subscript, or suffix, my bad. So this would be propanoic acid. So we take propane, instead of the E, you add the oic acid. So carboxylic acids are all named that way. You're just dropping the E and adding oic acid. Now, when we form our compound here by esterification, a dehydration synthesis reaction, what is our product going to look like? Well, we are going to lose H2O, right? We are going to be losing H2O. 1 hydrogen here, 1 hydrogen here, 1 oxygen here, in order to produce our final product. And our final product is going to look like this. Right, now we have that ester group present within our compound. So how do I name this compound? Well, we are going to take the alkyl name of our alcohol, which is what? What is it? Since it's a 4-carbon chain, the alkyl group would have been butyl, right? If we had a 4-carbon substituent group off of a hydrocarbon chain, we would call that butyl. And we are going to take our acid name, propanoic acid, and change the suffix from ic to ate. So that will be propanoate. Okay, propanoate. So what is the name of our ester? Our ester is called butyl propanoate. I know that was a lot to take in today. If you have any questions, do not hesitate to ask. But that is the end of chemistry this semester. It was a pleasure teaching all of you. I wish we could have done a lot of this in person. I wish you all the best next year. Keep in mind, next week, the week after, you can still come in via appointment. So if you have any questions about the course at all, or maybe you're thinking of chemistry next year and you have some questions about what do I really need to know from a grade 11, I would love to see you and I would love to chat. Right on, everyone. Have a wonderful day and enjoy your summer.